One way in which the hardware can help the operating system managing the memory while checking for correctness, while ensuring everything is done in the right way, could be through base and limit registers. Okay, this is a very simple approach, but it allows us to start observing how the hardware can help. So we know that in memory, we use some portion of the memory for keeping the operating system, and then we have portions that are actually used to maintain the information of the process. Okay, so for each process, we could define two numbers, basically two addresses. The base one, which is the one at which the memory used by a specific process starts, and the limit, which is basically what could be what you need to sum to the base to reach the final address, or the final address, it doesn't really matter. And now what we can have is two registers, one in which we will keep the base address and one in which we keep the limit, okay, and use these registers to check if a process is accessing its own memory or trying to access others' memory, okay? So this is an example about a process A. It has a specific range of addresses that it can access. And one way to go here is to use the hardware, to define an hardware that does like this. When the CPU tries to access a specific address, the first thing we check is whether the address is greater than the base address. If it is, then we check whether it's less than the base plus the limit. If it is, then we let the CPU access the memory. Otherwise, in any of the other two cases, we let the hardware generate a trap, generate a message, an alert, so that the hardware itself can stop once it is done with the execution of this instruction. And when it goes to checking what should be the following instruction, it goes and senses the interrupt line, sees there is such an interrupt, wakes up the operating system, and lets the operating system take a decision about what to do with this process that is trying to access memory that does not belong to it. Now, the important thing here is, of course, to define these two registers or the operations we want to do with these registers, basically to read and write, especially to write the values of the base and the limit register as privileged instructions, which means that only the operating system, when it's running in kernel mode, can change these addresses. We can do this during a context switch, while the user cannot change them, which means that as long as the user or the process that is run by a certain user tries to access memory, that does not belong to its own process, the operating system will wake up and do something about it, kill the process or create an alert for the process, and so on and so forth. Now, we actually know that the operating system is more powerful than any other process because it can run in kernel mode, and it can, of course, not only read the memory of other processes, but also modify the registers that refer to other processes without restrictions. And we already saw an example of this, and now you probably should understand why things are starting to fit together. In this example in which we had the fork and we were creating a new process and then calling exec to replace the memory, you can see that now when you replace the memory of the process with another, with other information, with information that belongs to another program, the amount of memory that the new program will need is not necessarily the same, which means that you might need to change the base or the limit register, depending on where you place the new information. And you can imagine the operating system is the one that is doing this, and that's why you give power to the operating system through the system call fork when you create a new process, or in this case through exec when you want to replace the memory of the new process.